Whenever a finger touches a surface, an invisible impression is left on it. This invisible impression is called latent fingerprint. Latent fingerprint is made up of sweat residue. To make it visible, we have to render color to it, and this is usually done by reacting one or more constituent of sweat with a suitable reagent. Amino acids constitute a very important component of sweat. They have several advantages. They don't migrate with time, so that old fingerprints can also be developed provided we have a reagent which reacts with amino acids and produces a colored compound. The most important reagent in this category is ninhydrin. It gives a complex called Rohmann's purple, and as the name implies, it is purple in color, so that the colorless amino acids and proteins of the sweat are converted into a purple colored derivative, which is very intense. Unfortunately, Rohmann purple is not fluorogenic in nature. Fluorogenic means that when a light source is used and light of a particular wavelength is impinged, it starts shining. But Rohmann purple can be made fluorogenic. If we react it with zinc chloride and then examine it under laser at a low temperature, a zinc complex of Rohmann purple is formed, which is fluorogenic. So that if the print is weak, if the color which comes with ninhydrin is not so intense, it can be enhanced and a sharp fingerprint can be developed by this procedure. Apart from ninhydrin, there are several reagents which react with amino acids and directly produce fluorogenic compounds. These compounds need not be colored. To the naked eye, they may not be visible. But when we impinge ultraviolet light or laser light on them, they start shining and a photograph can be taken. Examples of fluorogenic reagents include fluorosamine, 2-Phthaladehyde, DFO, ANS, and many more. All these react with amino acids, and the complexes which are produced, they may be faint in color, they may be even colorless. But when they are subjected to conditions of fluorescence, they emit a particular light, and technically we say that the fingerprint becomes sharp, the fingerprint is enhanced, and a good photograph can be taken. The advantage of this method is that amino acids are quite persistent. They are not destroyed by weather conditions, and as I said earlier, if the surface is porous, they do not migrate within the capillaries of the surface. They remain where they are, so that old fingerprints can also be developed. And if the fingerprints are faint, if they are fragmented, if they are weak, as usually is the case, then with the aid of fluorogenic reagents, we can make an attempt to develop such fingerprints also and make them visible and sharp. There are some fluorogenic reagents which impart an additional advantage too, and that is that suppose the fingerprints do not develop, still other methods of detection techniques or detection techniques can be used thereafter as post-treatment.
Dear students, after learning this module, you shall be able to know about fluorogenic reagents which interact with sweat residue, mainly amino acid, to produce luminescent products. Then you'll learn that the fingerprint developed by these reagents may be enhanced by illumination under a light source. And finally, you'll come to know that the fluorogenic reagents that have proved most advantageous in developing latent fingerprint. Now, let us start with introduction. Amino acids constitute an important ingredient of human sweat. When a finger touches a surface, these analogues are deposited thereon as sweat residue. This deposition, called a latent fingerprint, contains several other chemicals such as inorganic ions or organic derivatives. However, Unlike other sweat constituents, amino acids neither interact with the cellulose component of paper, cardboard, wood, and other porous surfaces, nor do they migrate within the substrate. As a result, reagents that have given colored derivatives on interaction with amino acids render visibility to both fresh and old fingerprints on a wide array of surfaces. Amino acids within the sweat residue are known to interact with a number of fluorogenic reagents to yield luminescent products when illuminated by light of a specific wavelength. These products shows intense fluorescence. As a result, it becomes possible to detect weak, faint, and chance fingerprints that are often found at crime scenes. Now, let me tell you something about the fluorogenic reagents. Here is enunciated a list of reagents which interact with amino acid constituents of sweat residue to produce luminescent derivatives, which in turn visualize latent fingerprints. Number one is fluoroscamine. Fluoroscamine is a spiro compound that is not fluorescent itself but reacts with amino acids to form highly fluorescent products. Hence, it has been used as a reagent for the detection of amino acids and peptides. It is also a fingerprint development reagent. A solution of 20 mg fluoroscamine and 0.4 ml triethylamine in 100 ml acetone is sprayed on the surface containing the finger mark. The surface is dried and observed under an argon laser. Sharp and clear fingerprints can be rendered visible. Second is 2-phthaldehyde. 2-phthaldehyde reagent, the structure of which is set out in the figure, is used as a very sensitive fluorescent reagent for assaying amines or sulfhydryl in solution, notably contained in proteins, peptides, and amino acids. As a result, it also reacts with amino acid and protein components of sweat residue to reveal latent fingerprints. On examination under an ultraviolet lamp or an argon laser, the developed prints are enhanced due to fluorescence. Two solutions are required when 2-phthaldehyde is to be used as a fingerprint reagent. Solution A is prepared by dissolving 2.5 gram boric acid in 95 ml distilled water. The pH of the solution is adjusted at 10.6 with 6 potassium hydroxide. To the solution, 0.3 ml of 30% detergent and 0.2 ml 2-mercaptoethanol is added. Solution B is prepared by dissolving 200 mg 2-phthaldehyde in 2 ml methanol. Solution B is mixed with solution A. The mixture is then sprayed on the exhibit. On drying, the surface is examined either under an ultraviolet lamp or under an argon laser, whereupon fingerprints are rendered visible. Third is dancyl chloride. Dancyl chloride, the structure of which is depicted in figure, reacts with primary or secondary amines, amino acids, and proteins to produce stable blue or blue-green fluorescent sulfonamide adduct. It is widely used to determine protein sequencing and for amino acid analysis. It may also be used to label hydroxyl and carboxyl acid functional groups. In forensic applications, it is a fingerprint reagent. For detecting latent prints, the composition is prepared by dissolving 10 mg dancyl chloride in 20 ml acetone. The solution is diluted by adding 80 ml Freon. The test solution is sprayed onto the surface and allowed to dry. Clear fingerprints can be observed upon ultraviolet illumination. D is 4-dimethyl aminocinnamaldehyde. The structure of 4-dimethyl aminocinnamaldehyde is shown in the given figure. The test solution is prepared by dissolving a mixture of 4-dimethyl aminocinnamaldehyde and sulfuric acid in ethanol. The solution is further diluted by adding ether. The mixture is sprayed on the article, and on drying, the fingerprints may be observed under ultraviolet or laser light. The background coloration, if any, may be reduced by keeping the developed prints in the dark for a few days. The reagent is, however, not good at developing old prints. 4-dimethyl aminocinnamaldehyde may also be used as a fumigant for visualizing fingerprints on a wide range of surfaces. Next is 4-chloro-7-nitrobenzo 2-oxa-1,3-diazole. The 4-chloro-7-nitrobenzo 2-oxa-1,3-diazole is used for fluorogenic detection of latent fingerprints on multicolored paper. About 0.1 gram 4-chloro-7-nitrobenzo 2-oxa-1,3-diazole is dissolved in a mixture of 10 ml acetone and 90 ml fluorizole. Colored paper is dipped in the solution for a few seconds, air dried, and heated at 80 degrees Celsius for 2 minutes. The developed prints are examined with blue light and observed through a 580 nanometer orange filter in a dark room. Then another method is 8-anilinonaphthalene 1-sulfonate. 8-anilinonaphthalene 1-sulfonate has proved to be a valuable and sensitive reagent for detection of fingerprints on greasy and porous surface. The developed fingerprints, when impinged with long wavelength ultraviolet light, show bright yellow fluorescence against dark background. Rapid development, no heat requirement, and simplicity are some of the other advantages of this technique. About 1 gram of 8-anilinolaphthalene 1-sulfonate is dissolved in 5 ml methanol and the resulting solution is mixed with 200 ml Freon. After the two layers separate out, molecular sieves are added to remove methanol as it causes running of ink on scripted documents. After spraying the test solution on sample fingerprints, the surface is allowed to dry for about 1 minute. Then examine under long wavelength ultraviolet light, whereupon fingerprints are rendered visible. Another reagent is 7-nitro-4-benzo-furazanyl ethers. 7-nitro-4-benzo-furazanyl ethers are fluorogenic reagents that can develop latent fingerprints on paper with a high degree of sensitivity. These may be used both in solution form as well as in vapor phase. Although the development is faster when a solution of the reagent is used in vapor phase detection, there is smaller background fluorescence and discoloration. The most important compound of this classification, which is mostly used for latent fingerprint detection, is 4-methoxy 7-nitrobenzofurane. The spray solution is prepared by dissolving 100 mg of 4-methoxy 7-nitrobenzofurane in 1 ml acetonitrile and diluting to 100 ml with fluorozole. Samples bearing latent fingerprints are dipped into the test solution for 15 seconds and then air dried. These are then heated in an oven to 100 to 120 degrees Celsius for 10 to 15 minutes. Clear and sharp fingerprints develop. For vapor phase application, about 20 mg crystals of the compound are placed in a glass beaker and fingerprint samples are suspended about 15 cm from the base of the container. The beaker is covered with a thin aluminum foil and heated in an oven to 60 to 95 degrees Celsius for a period of 1 to 7.5 hours, whereupon the fingerprints are visualized. Another fluorogenic reagent is 1,8-diazafluorine 9,1. 1,8-diazafluorine 9,1 is an amino acid sensitive reagent which develops latent fingerprints on porous surfaces like paper and wood. On reacting with the fingerprint residue, it gives a pale pinkish purple luminescent product. The structure of 1,8-diazafluorine 9,1 is depicted in the given figure. The test solution is prepared by dissolving 0.5 gram DFO in 1 liter of methanol or petroleum ether. The surface bearing the latent fingerprint impression is immersed in the reagent for 5 seconds, dried, re-immersed for 5 seconds, and heated at 110 degrees Celsius for 10 minutes. Under white light, pink purple ridges are rendered visible. The surface is illuminated with radiation of 470 nanometer wavelength, and fluorescence is observed through a 570 to 600 nanometer filter. The luminescence is at its maximum immediately. The heat treatment and then decreases slightly with time due to the absorption of ambient humidity. The luminescence may be restored to its original intensity by reheating the prints. Another reagent is 1,2-indandione. The reagent 1,2-indandione develops excellent quality fingerprints on porous items by reacting with amino acid content of sweat residue. It is specifically useful for detecting prints on bank check and thermal paper. A test solution of the reagent is prepared by dissolving 2 gram 1,2-indandione in 70 ml ethyl acetate. The contents are diluted to 1 liter by adding 930 ml petroleum ether. The solution is sprayed over the article bearing latent fingerprints and then heated in an oven for 20 minutes at 100 degrees Celsius. The fingerprints so developed are illuminated with light of 515 nanometer wavelength and observed through orange goggles. Finally, these are photographed. Now, let us see the assessment of these reagents. The value of fluorogenic reagents for developing latent fingerprints emanates from the fact that these interact with amino acid components of sweat residue and produce luminescent products. Ninhydrin is yet another reagent which interacts with amino acid content of latent fingerprint residue. However, the product of ninhydrin amino acid interaction, Rumen's purple, is non-fluorescent. The reaction between ninhydrin and a representative amino acid is given in the figure. The fluorescent characteristic may be imparted to the developed prints by treating these with a group of 12-metal salt, generally zinc chloride. The resulting coordination compound, the structure of which is depicted in figure, shows intense fluorescence under laser light. Thus, although ninhydrin is an efficient and a very popular reagent for detection of fingerprints, optimum results are obtained only after post-treatment of developed prints. The fluorogenic reagents, on the other hand, produced fluorescent products in one step. Therefore, no post-treatment is necessary. Of all the fluorogenic reagents cited here, two are most promising. These are 1,8-diazofluorone 9,1 and 1,2-indandione. The results obtained with these two reagents are comparable to and sometimes even better than those obtained with ninhydrin. Both these compounds yield pale colored prints but produce strongly fluorescent details when illuminated by green light. It is now pertinent to make a comparison between 1,8-diazofluorone 9,1 and 1,2-indandione. Each of these have a few merits as well as shortcomings. For example, 1,2-indandione is more easy to synthesize, has a lower cost and better solubility than 1,8-diazofluorine 9,1. 1,2-indandione fails to develop fingerprints on recycled paper items like newspaper, while 1,8-diazofluorine 9,1 is successful on such surfaces. 1,2-indandione develops good quality fingerprints on thermal paper, while for 1,8-diazofluorine 9,1 this is a problematic surface. Dear students, let us now summarize this chapter. You see, in this chapter, we have learned that latent fingerprints may be visualized by a legion of amino acid specific reagents. And again, we have come to know that fluorogenic reagents interact with sweat residue, mainly with amino acids that are present in sweat to produce luminescent products. Over the years, ninhydrin has been branded as the most efficient amino acids tagging compound as far as detection of latent fingerprints is concerned. However, the reaction product of ninhydrin and amino acids is non-fluorescent and only after post-treatment yields luminescent product. Then, we have also learned in this chapter that the fluorogenic reagents are advantageous in that these produce fluorescent derivatives on reacting with amino acid content of sweat residue in only one step. That is how it saves our time as well. And then lastly, we have learned that two fluorogenic reagents, that is 1,2-indandione and 1,8-diazafluorone 9,1, have been validated for detecting latent fingerprints on porous surfaces. The detection methodologies have been standardized, and these procedures are being used in casework investigations.